Something out there has the mass of 1,000,000 suns, and almost everything about it is wrong. It does not shine. It does not look like a normal galaxy. It does not behave like the kind of small dark matter clump cosmologists usually expect. It was not found because anyone saw it directly. It was found because gravity betrayed it, by twisting a distant beam of radiolight in a way that should not have happened unless some hidden mass was sitting there in the dark. And the more carefully astronomers reconstruct that hidden object, the harder it becomes to place inside any clean category we already trust. The object lies in a gravitational lens system called JVASB 1938 plus 666, far beyond the Milky Way, at cosmological distance. A foreground galaxy bends and magnifies the light from an even more distant background radio source, stretching that background emission into thin arcs. In one of those arcs, astronomers found a local distortion, a small gravitational wound in what should have been a smoother pattern. That distortion was not random noise. Detailed modeling showed that some compact dark perturber had to be there, adding extra gravity on top of the main lens. The inferred mass was about 1.13 million times the mass of the Sun, enclosed within a projected radius of about 80 parsecs, around 260 light-years. That alone would have been enough to make the discovery important. Detecting such a low-mass dark object through strong lensing pushed the method into a regime roughly 100 times below previous cosmological detections of comparable substructure. This was not just another blurry hint of dark matter in bulk. It was a sign that astronomers had started probing the small-scale architecture of the dark universe in a new way. Not by waiting for dark matter to emit light, which it apparently does not, but by measuring how precisely it scars spacetime. At first, the story still had a relatively ordinary interpretation. Standard cosmology, the lambda CDM model, predicts that galaxies should sit inside much larger dark matter halos, and that many smaller dark subhalos should also exist around them. Those subhalos are not supposed to glow on their own, unless they manage to collect enough normal matter to form stars. So finding a dark object on this mass scale was exciting, but not automatically catastrophic. It could have been one more data point for the existence of low-mass substructure. The problem was that this object did not seem to want the shape that a simple dark matter subhalo is supposed to have. That is where the second act of the story becomes much stranger. On January 5, 2026, researchers at the Max Planck Institute for Astrophysics reported that when they studied the object's internal density profile more closely, the usual picture fit poorly. The mass distribution did not look like a straightforward diffuse clump. Instead, the reconstruction pointed towards something more structured, a very compact central component, compatible with something like a black hole or dense central concentration, sitting inside a broader, more extended, disk-like mass distribution. Not a simple point, not a simple puff, something with internal architecture. That is the real source of the tension. A compact center by itself would not be shocking. A broader dark halo by itself would not be shocking. But getting both together, in an object with no clearly confirmed luminous counterpart, is deeply awkward. It starts to resemble a tiny galaxy in terms of structure, except a galaxy normally gives itself away. Stars leak light. Gas leaves signatures. Dust absorbs and re-radiates. Ordinary matter has ways of being noticed. Here, gravity is telling astronomers that something organized is present, while the object itself remains essentially dark. It is not just hidden mass. It may be hidden structure. That does not mean cosmology has collapsed. It means the easy explanation has. The original 2025 analysis already found that fitting the perturber as a standard Navarro-Frank-White style halo required an unusually high concentration for its mass. The later work tightened the discomfort by showing that the inferred profile may be better matched by more complex scenarios. One possibility is that this is an extreme, but still technically allowed dark matter-dominated substructure. Another is that it is telling us the small-scale behavior of dark matter is not as simple as the cold, collisionless baseline picture assumes. The object sits right in the territory where dark matter models begin to disagree with one another most strongly. This matters because small-scale structure is one of the few places where dark matter physics can still be pressured directly. On large scales, different dark matter models can produce a universe that looks frustratingly similar. Galaxies form, clusters form, cosmic structure grows. But when you zoom in to much smaller masses, the differences sharpen. Warm dark matter, fuzzy dark matter, self-interacting dark matter, and ordinary cold dark matter do not all predict the same abundance, concentration, or inner density profiles for low-mass objects. That means a single dark perturber of about 1 million solar masses, if measured precisely enough, can carry information about the microscopic properties of the dominant matter component of the universe. And that is already happening. Follow-up theoretical work has not treated this object as a curiosity to be filed away. It has treated it as a serious test case. One recent study explored whether a fuzzy dark matter soliton core combined with a central black hole could reproduce the reconstructed structure. Another found that self-interacting dark matter can fit the inferred profile better than a standard NFW-like halo. Neither of those ideas has won. Neither is established as the answer. But their very existence tells you how unusual this system is. Researchers are not just asking how to name it. They are asking what kind of dark matter could build it. The way the object was found makes the story even more severe. No one imaged this thing the way you would image a star or nebula. What astronomers actually measured was a disturbance in an arc of radiolight. General relativity says that mass bends spacetime, and in a strong lens system, that bending can magnify and distort a background source into arcs and partial rings. If the mass distribution along the line of sight is perfectly smooth, the lens pattern is correspondingly smooth. If an extra dark object is sitting there, even a relatively small one, the arc can be pinched, shifted, or scarred. That is exactly what happened here. The object exists because the geometry of light says it must. There is something profoundly unsettling about that. We are used to learning about the universe by seeing things glow. This is different. Here, space-time itself becomes the detector. The hidden object never introduces itself. It is identified because it bends somebody else's light at exactly the wrong place and by exactly the wrong amount. It is the astronomical equivalent of finding an invisible animal in fresh snow, only because the footprints are too deep and too strangely spaced to belong to anything you know. The disciplined version of the story is not that a shadow universe has already been discovered. It is not that dark galaxies, primordial black hole swarms, or exotic hidden sectors have been proven. None of that is established. The disciplined version is narrower, and for that reason, more powerful. Astronomers have found a real gravitational perturber at cosmological distance, with a mass of roughly 1 million suns, and the current reconstructions indicate a density profile that standard interpretations do not explain cleanly. That is enough. Science does not become interesting only when the answer is known. Sometimes it becomes most interesting when an object is real, measurable, and still resistant to classification. What happens next is what will decide whether this becomes a famous outlier or the beginning of a much bigger problem. Astronomers need more lens systems, more high-resolution arcs, deeper searches for any faint luminous counterpart, and a larger population of dark perturbers on this scale. One object can always be argued over. A population is much harder to dismiss. If more of these compact, structured, nearly invisible objects begin to appear, then the pressure will shift from the data to the theory. Dark matter will stop being merely the unseen mass that holds galaxies together and start becoming something with measurable internal texture. For now, this object remains suspended in that rare and valuable state between discovery and explanation. Its mass is real. Its gravitational signature is real. Its structure appears real. But its identity is still unsettled. And that is why it matters. Even now, In a universe we like to imagine as increasingly mapped and understood, something dark, massive, and structurally strange has revealed itself only through the mark it left on bent radiolite.